Welcome back. Welcome to the bonus video series. So in this final series of videos, which I appreciate you paying for certification, so we thought we'd give you something extra. The topic I'm going to cover is regression. And simply stated, regression is building a model in which we can predict one variable based on one or more other variables. And we start with our house prices original file. And of course, the first thing I'm going to do is save it as a new file. We'll call this house prices -B1 for bonus video 1. I feel like a game show host talking about bonus videos. So what are the things that would likely impact the price of a house? Well, the size of the house for one, and the lot size. And in different parts of the country, the lot size may actually be more important than the size of the house. But, unless it's a populated area, the size of the house is probably going to be dominant. And that's my hypothesis. So what I'm going to do is insert a space next to garage, and I'm going to copy the price column into G. And I'll tell you why I'm doing that in a minute. The other thing you might want to note is I am missing the square footage for house number 23. So we'll probably blank out that data. Let's blank it out now so we don't forget. So now we're only dealing with 38, and I'll make that yellow. Sometimes I do that to remind me when I've changed something. So here, one of the things I want to do is visually see the relationship, and that's a scatter plot. So when you're dealing with multiple variables, one of the best ways to take a look at them is to develop a scatter plot. And one of the reasons I put price over here is if I start with square feet, and then I go up to price and I hit Control and highlight and drag down the price column. Remember, I got to have the Control button held when I do this. Then I can insert a scatter plot. Very simple. And there you see, which we'd expect, as the size of the house gets larger, the price gets higher and higher. And save for a few potential what we might call outliers, that makes a pretty good line. And this was done with real data. So here is a smaller house, maybe 11 or 1200 square feet, and it priced out much higher. So maybe there's something unique about that house. So here we have the visual relationship. We can now add a trend line by clicking on any one of the dots and then right-clicking, add trend line. We've done this before. I got to scroll down a little bit. I want the equation and the r squared. And then I can close this out. So what this tells me is that for every additional square foot, I'm going to see about $60 more in price of the house, which is not too far off reality. So we start with a baseline of $85,000, and that increases by $60 for every square foot. And we'll get more into that after we develop some of the models. So now, the second part that I added is something called the r squared, or the coefficient of determination, or coefficient of multiple determination, if we had more than one variable. Now we're going to explore multiple variables or multiple predictors, like using the square foot and the lot size at the same time, but it's really hard to graph that without some special software. So here you see the visual. It's a pretty good fit, and the way to read this is that's just about 75%. So that r squared value here means that 75% of the variation of the house price can be explained by variation in the house size, which is pretty good, taken all by itself. So that is our first display. And now we're kind of getting into a level where let's now compare that to the display for the lot size. I'm going to try and get those two displays right next to each other. Now, the second go around, oops, I thought I had that highlighted. So I want the lot size and the house price highlighted. Then I go back and I insert another scatter plot. Now you can kind of see the comparison. Not quite as good a fit. It does seem like there is some relationship, but not nearly as good. So I'm not expecting a high R squared. Oh, and by the way, R squared is indeed the square of R, which is the correlation coefficient. But now we've got the price over here. Again, I can click on it. I can add a trend line, scroll down. I want the equation in the R squared. Let's get rid of that box so we can see things more clearly. There's a joke in there somewhere. Maybe I can move this box a little bit up. So here we see in this case the constant, or the y-intercept, is almost 165,000, and each acre is worth almost 75,000. That's a big difference in terms of how the slopes look. And we don't have nearly as good a fit to a line, as exemplified by the fact that we have an R squared value that's only 27%, which means that only 27% of the variation in lot size can explain the variation in house. So our initial takeaways here are we see a better fit for the square footage, not quite so good a square foot fit for the lot size. And it's a nice little comparison. By the way, if the fit is inverse, that is, perhaps if we had the age of the house, the older the house, the more repair and maintenance it might need, we could see a downward slope. In a regression, we're equally happy to have a strong downward or negative or inverse relationship as we are to have a positive relationship. The key is how well do the points fit that line. So now, let's see if we can replicate that regression line, and we'll start with the square footage. So I go back to my data set. So I'm going to scroll up here. And in this case, I'm going to copy everything over to a new tab, and I'm going to say regression. And I'm going to paste it in. Maybe make it a little bigger. And now I'm going to save this because I haven't saved it in a while. In this case, I am going to start with the price. First, I'm going to get rid of some of the other things, like everything I don't need. I want to make sure we still have that blank. Oh, and I can get rid of those displays too. Great. So I'm now going to add 3 rows at the top. And so if you recall, I'm trying to get this regression equation of 0.0601 plus 0.573. Let's see if we can make that. So what I need to do for that is have a constant and a slope. For, in this case, we'll call it x1, where square feet is going to be x1. And as you may know by now, I'm very anal about these things. So I'm going to write justify it. Now, if I assume a starting slope of 0, a starting y-intercept of 0 and a slope of 1, basically what I'm saying is that I've got a 45-degree line going up. And think about that. So that's my starting point. We're going to adjust that later on. And let's see, I suppose I could format that here, but for the slope, I probably want at least 2 decimals. Okay, so I've got my 2 columns. The next thing I'm going to do is I'm going to make column D, E, and F a little wider. Maybe need to offset it a little bit. So for column D, E, and F, I'm going to have something called a predicted Y. All right, where the predicted Y is going to be the Y value based on an equation that's basically 0 plus 1 times X, where X is going to be the square feet. So I can do that by saying, okay, start with the constant in B2, and I'm going to anchor that with dollar signs, plus the slope, also anchored with dollar signs, times the value of X, which is in column C. So here, my predicted Y value is 1,475. I'm going to copy that down to row 39. Oh, and I should get rid of this. And I should probably get rid of all of row 23. I apologize for that little snafu. And I found an error. That should be, let me start that formula again. So let me go here. That should be equal to B2 anchored plus C2 anchored times the X value here. That makes more sense. Let me copy that down. Sorry about that. So now we have, and one of the reasons I knew that it was wrong is these two numbers match if you think about it. So perhaps over here I can say that price equals 0 plus 1.00 times square feet as a starting equation. Okay, now we're getting somewhere. Now what we're going to look at is the difference between our actual Y value and our predicted Y value. Typing would be good. And all right. Another thing I might do here is go back to my freeze pane. So I go to View, Freeze Panes. I've done this a number of times. That'll make it easier to see what we're doing. And I'll write justify that. That's just window dressing. Don't lose any sleep over it. So my actual Y value is the price minus my predicted Y value gives me my deviation. So right now I'm way over. That's okay. And then the next column, I'm going to copy the title over here, is going to be squaring my deviations. So now I've got squared deviations. If I take the value in column E and just raise it to the power of 2, I now have my squared deviation, which I agree is very high. Let's move that down to just 1 decimal. That's why I made some of the columns wider. So I have 3 new columns: my predicted Y, my deviation or difference or residual, and then my squared deviation. So I'm going to copy that down and in column F, I'm going to sum that. So that is the sum, the SSE. I'll explain, hang on. And the SSE is the sum of the squared errors. And that's my big thing here. So I'm going to highlight all this and make it bold just so you can see how it all ties together. Now, do we want to have a large squared error or a small squared error? Well, if you recall, we had a slope of 0.06 and a y-intercept of 85. I could change that here and wow, let me do that again. It started at 0 and 1. My squared error was 154 million. Be great if I had that in the bank, but that's not helping me here. So I'm going to start with what I had off the other one, 85 and 0.06. Don't forget those are in thousands of dollars. And look how much lower I was able to reduce my squared error. Way down to 42,000, which is probably pretty reasonable, which is probably pretty good because of what we did. Now, I can hone in on that a little bit more, but let me save this first. So the next thing I'm going to do is go back to Solver. So click on Data, then Solver. If you note, I left my pointer in cell F42 or 43, and I want to minimize the value at F43, which is the sum of the squared errors. That's my goal, is the line of best fit, the regression line, is the sum of the squared, is by minimizing the sum of the squared errors. So here, I'm going to allow Solver to manipulate both of those, which I know are pretty close. I don't know if I'm going to get much more reduction, but I wanted to start here to show you. And then I just say solve. And before I say OK, it looks like I got a little bit of rounding, but pretty darn close to the beginning number. And I'm going to say OK. I could maybe add a decimal here to show that it is indeed 0.06, which is about $60 per square foot. That's not too bad. So let's end this here. And perhaps what I'll do is just remind you here that as a final equation, and these are somewhat small approximations, 86,000 plus 0.060 times square feet as a final equation. So there's sort of the background that can help you figure out what the line of best fit is. And you can do this with any pair. See you in the next video.